Like to reject.
Okay. Then we would like to challenge you to problem number 1, paper boomerang.
I think. Can they still challenge this problem even with?
Yes, you can.
Oh, we like to reject.
Okay. Then we would like to challenge you to problem number 4, climbing magnets.
We like to accept.
Okay.
They got 1 8. They got 7 and 6. And they got 1 1 6. It's recorded. Bunch of bigger.
Yeah, I saw like they were really good.
I mean, they
Please write down your names on the board.
Just
a vertical horizontal magnetic rod, and we limit the motion of the magnet to a vertical direction. So when the vertical rod is spread around in vertical symmetry, the magnetic rod begins to turn up. So we can explain this phenomenon and explain kind of rate of turning depends on random parameters. So again, you put it here to be a force because the magnet comes upward, and also the maximum each parameters and the motion of the magnet. So first of all, let's listen to the layout for today. So we're talking about the phenomenon and setup. So we just run around this rod, and you can see that magnet is actually coming up, and there's a three directions of motion. The first is you can see that magnet starting to rotate, and also it has a translation climbing up, and also you can see that in the x direction it is a little bit oscillating. So you can also see that there's angular velocity one also oscillating, and also this is also oscillating. And also, if the number of magnets is too small, it becomes too high to prime, and if the number of magnets is too large, it becomes too high to prime, and so it will fall down. And only because it's stable, you can see that the magnet will be climbing up. And also, in climbing region, you also have a stable part and unstable part. As you can see that for stable part, the magnet will always climbing up. However, in the unstable part, the magnet sometimes might descend. And you can also see that from the side view, the magnet for stable part it always have a magnetic line. However, for the unstable part, sometimes it will become a magnetic point instead of line. And here is the geometry and the setup. And for the geometry, you can see that we use the port to limit the motion of magnet to a vertical direction, and we also observe the rotational motion for assembly label. So here comes to the theory, which is the EMO of the magnet. So first of all, since that there is a three direction of motion, we consider about three direction of motion. And this is for the x direction. And also, we can consider about the gravity torque causing the magnet to belong to descending. So we can derive 4 equation here. And this actually is not considered inversion, as you can see. It is in these three motion, direction of motion, it's all of the friction between a rod and magnet over here. So it's pretty important to know about the friction. So here, I'm going to talk to you about friction between the contacting line. Since the friction direction is related to a velocity of contacting line, so we consider about the fourth direction of motion, which is responsive for kind of velocity. And then, so if you can see that for friction, it actually has a vertical direction and a horizontal direction. And first of all, for horizontal direction, it's actually while crossing, there's to be a friction torque, since the rod is spread in this direction, and we're crossing a friction in this direction. So if you fix point over the port, so we limit the magnet for the vertical direction, it actually causing that the magnet will start to tilt. And if the magnet is tilting too much, it will actually induce another magnetic force making this magnet tilt back to a more vertical angle. So it will actually causing that the magnet has the x direction oscillate. So you can just derive it from this formula and the oscillation. However, we can see that this will come to this phenomenon, since that it will magnet will stick to rock during the torque, the tilt, and will insert back when the intention is tilting much. And also, for the standard formulas, we consider our normal force distribution. Because there is a magnetic force, one of the magnets are descending, so the normal force will distribute equally. You can see that, right? By increasing the number of magnets, we're actually causing that the normal force become more equally. So the normal force downward has become larger. And this normal force distributed equally, but relevant to the magnet rotate. Because that if the rod is start rotating, you're actually causing that friction, making the magnet start to rotate. And you can see friction here is actually distributed unequally. So you are causing that friction to torque. But after the magnet starts to rotate, you are actually causing another velocity, causing that the magnet will resist rotating. So you are causing a friction to resist the magnet rotating, and it corresponds to the x displacement over the contacting line between the center point and the contacting line. And also, we can then learn about the velocity, the contacting velocity, since that we can just simply calculate it. So this one is actually the contacting line velocities. So if the contacting line velocity is upward, we're causing the friction downward. And the contacting line velocity downward, we are actually causing the friction here upward. So we are making the magnets of driving. As you can see, also see that here is the instrumental data. You can see this is the contacting line velocities, and here is the displacement. You can see that when the actually it is more velocity you are causing the displacement going up to a faster. And also, this is instrumental data. Also, you can see that for this is translation velocities. It actually has a oscillating part. And also, you can see the maximum velocity corresponds to the stepping part, and the minimum velocity corresponds to a stepping part. So here comes to the third property of the magnet. So first of all, we just simply call the translation acceleration and the translation velocity here. We can see that it is actually a step loop of simple harmonic motion, which means that we can just simply assume that the velocity equal to the cosine function adding a constant term, because there's the main velocity is not equal to 0. And also, we can just simply assume that the acceleration here should be at the same function, and we can just know that the pace of turning up the velocities is actually the constant linear growth adding a sine function. And also, we plot the converting velocities and translation acceleration together, so we can see that it actually has a little tip on the angle, and it's because that there is a phase difference between the converting velocities and also the accelerations. So adding this condition, we can just simply get a simple velocity model for the Hawking magnet. We can see that the velocity here is actually equal to constant term adding an actual constant the dynamic term adding a constant term. And the constant term represents the actual traveling rate. Because if we take the average of the velocities, the velocity here was here. So actually traveling rate is mentioned here. And this function is actually corresponds to a specific phenomenon. And also we can add some assumption we just mentioned above. So then we can get the velocity here. Velocity here should be related to the kinetic velocities. However, we just replace the parameters here to replace it for like the omega x, which is the rotational velocities, and the s is vector, which corresponds to the x direction displacement. So also to plot the base diagram, because we mentioned that there's if the number of magnets is too small, it will become too rectangular. So that corresponds to this blue region, and then too heavy, it corresponds to the upper region here. And also we can see that there's a coming stable, which is always become magnetic line, and coming unstable, which is corresponds to any kind of magnetic point. And for the having unstability, you can see that sometimes there might be only a magnetic line, or magnetic point over here. And it's because that if the number of magnets not too much, the property like the magnetic force cannot support the magnetic force. So it will show that the magnet will be tilted. And since they will be tilted into only one magnetic point, so it will show that the magnet is rotating downward. So it will show the descending. Also, you can see that the magnet only descending while the angular velocity is increasing. So this is something actually correct, and it is the reason of the unstable part. But since the unstable part is kind of quantified, so in the video below, I'm just telling you about the stable part. And here is the turning velocity of the magnet. First, we just separate the traveling of magnet into two parts, which is the steady part and the slipping part. And then you can first see that in the faster velocities, it's actually not related to the number of magnets. However, if it increases the number of magnets into a region, you are supposed to reach a stable region, you can see that there is a sudden velocity drop here, and here. Okay, which means that these two regions are actually not distinct mechanism induces, so we just mentioned before. And also, for the slow region, which is corresponds to slow velocities, you can see that the number of magnets still not influence the velocity a lot. However, also we can just just obviously seeing that there is a sudden velocity drop between the stable region and the unstable region. And also here is another parameter about one angular velocity. So we will just change the one angular velocity to making that a kinetic line here has a larger velocity between the rod and the magnet. You can see it. Actually, if I increase the rod angular velocities, it will influence the magnet angular velocities first. So we can see that it is actually a linear relation, and if we just use the formula here, you can see that the slope here and the area is quite like the treatment here. So actually, if I increase the rod angular velocity, it will first increase the magnet angular velocity, and then the magnet angular velocities will increase the traveling up velocities. So yes, we can just simply replace the angular velocity into this formula, so you can see that the actual traveling rate is related to the rod angular velocities. And also the linear relation is related well to the theory also. And then it's rod diameters. And actually, these two parameters are kind of similar because the rod diameters and the rod angular velocities are influence the velocity between the rod and the magnet will always have this multiply also. So also if I increase the diameter of the rod, it will actually increase first the magnet angular velocities. So if I have this also linear relation method, and we still have a good agreement with the theory, and rather this however, if I increase the magnet angular velocity, it will then increase the Hamming rate. Then you can see I have also a linear relation here. You can see that the actual Hamming velocity with the Hamming rate is linear relation to the radius of the rod. We still have a good agreement with the theory. And then we will change the displacement between the cord, which is limit the motion for the direction, and the bottom of the magnet direction here. So actually, if I change the distance between this, it will actually influence the S displacement, the quantum displacement over here. So in this sense, then if I change the E to correspond to the moment R of friction. So actually that has another X direction, X direction of state energy. You can see that we increase D, but consuming energy become larger. And since that the X displacement of state will become larger, will influence the actual Hamming rate larger. There's also a linear relation between the Hamming rate, and it's not actually a linear relation, but because this number is pretty small, so we can just assume that this is a linear relation, and it's quite big also. So here comes to our conclusion. So for modeling, we just consider about 4 types of motion, 4 directions of motion for friction model. And also for scissors phenomena, we can see that we can observe the actual the simple harmonic motion rule for the base diagram, so we can just see that velocity equals to equilibrium, which is the scissors phenomena, and the actual Hamming rate with the constant. And we will have a solidity standard for unstable condition, and just compare the parameters and these effects of the parameters. And then the whole line will be.
Hello, my name is Muzela Labikova, and I will be the opponent today. I have a couple of questions for you. So first of all, can you list all the assumptions you have made in your theory?
Cool. Sure. The main assumption for a sample velocity theory is actually here.
Okay, and what does it mean qualitatively?
What do you mean?
Like qualitative meaning of the assumptions.
Like the first, like this meaning is that because acceleration is actually oscillating, and the type rate of oscillation is actually moving to zero in response to the actual rate.
Okay, so the system doesn't accelerate, the magnet don't accelerate. That's the main assumption, right?
Yeah.
Okay, thank you. My next question is, do you have some sort of prediction for slides 23, 24, 25, or 17? Or so like quantitative prediction?
Like prediction?
Yes, like for these measurements you have.
Oh, since that the amplitude here need to be using a numerical solution, it's quite complicated, so I can actually solve the amplitude here.
Thank you. In slides 10 and 14, there are multiple coefficients of friction mentioned. So what is the meaning of like the different coefficients of friction and how were they obtained?
What do you mean? Oh, so
Like there is on slide 14,
14?
say, or 10. Like, there is some mu,
so
there is FD, and various.
Okay, so the FE here is actually because we have a supporting core limit the motion to a vertical direction. So FE here is actually a version of the wall.
Okay, so you have like multiple coefficients of friction.
Yeah, we have a version between a rod and a magnet, and also a force with a magnet.
Thank you. On slide 30, can you show us the lines? 30.
Sure.
Thus, do the lines pass through zero? Because according to the equation, they should.
It should, but it has a boundary.
Will the total line pass
Yes,
through
of course it
zero?
should have a limit. It actually has a limitation.
Okay, so these are just fits, not from the equation?
Guys.
Okay, thank you.
we learned that often the happens miscommunication because they don't understand each other.
Study for an exam last Friday and you have to watch the lecture and do it. This is what it felt like.
That's why I've also learned how to speak. So, maybe on course, but
Okay, so hello, I'm with from Team Slovakia and I'm your opponent today. So this will be our opposition problem number 4, climbing magnet. So the reporter was supposed to investigate on what parameters the rate of climbing depends and explain the phenomenon. That is the main thing I would like to point out. So let's move on to the pros and cons of the report. So first of all, we have received long derivation of theory and explanation of theory where what was obtained from where, and the theoretical model seemed really complex. And in some graphs, we saw quantitative match of these experiments. However, since we have such elaborated model, I think there should be comparison in more graphs, not only on the graphs where we have seen the dependence of velocity or the rate climbing on the angular velocity, but also on the other graphs. And also what we found suspicious is that there was a linear equation on the graph, or plotted near the graph, and the lines on the graph were linear, but they did not pass to 0. So that's what I would like to discuss, why is it so, and why we don't have predictions for some other graphs. But for the experimental setup, it seemed really stable. We liked how the experiments were done, and it was really easy to track the velocity and the rate of climbing from the experimental setup. However, it is not clear if the fidget spinner or the points at the end of the rod were also accounted for in the theory in the moment of inertia. Because we believe that the fidget spinner at the end of the rod might affect the moment of inertia. Also, what was unclear about the theory was on some qualitative level what the assumptions were. How did he model the magnetic force? What did he assume? We have only heard in our questions that the main assumption is that the rod doesn't accelerate in its climbing rate. However, this also contradicts maybe the oscillations of velocity. Speaking of the oscillations of velocity, we would like to maybe elaborate more on that and see if really it is caused by the slipstick phenomenon. Because in the slipstick phenomenon, we believe that actually the motion should be somehow lagging. When it sticks, the magnet rod should not be rotating, and actually that's not what we think was observed. So it is also not proven enough, I believe, that it is actually slipstick phenomenon. But what we really liked about the theoretical model was that they did not neglect the tangential or horizontal component of the magnetic force, because it is, we believe, really important in this phenomenon, and otherwise the magnets would fall off. And also there was qualitative explanations of why the magnet shifts, because of the force that is acting from the However, it was also not clear if this force that is present from the barrier was accounted for in the theory. Also, what was weird was that there were multiple coefficients of friction, and it seemed like in x direction and y direction there were like different coefficients of friction. So that is weird. Thank you, and let's move on to the discussion. So maybe again, let's go slowly through the assumptions of the theory, and maybe somehow again clear up what you assume in the theory, like on a qualitative level.
I think there's a lot of assumptions made, so which.
Okay, can we list them? Maybe
Of course, so many.
write on the board.
Okay. So first of all, we assume that because there is simply there is a displacement between the magnet from the center of the magnet and the center of the magnet. So what actually tells us that there should be a like a magnetic pole.
Okay, there is torque from the boundary keeping it in vertical direction. Right.
Yeah.
Okay.
So then we assume that so induced you have a simple model since that we observe there is an oscillating x direction oscillation. So we just assuming that there should be like a linear relation.
We observe the oscillations. That's another assumption. But why do we observe them? Can you like state that?
So this is just like since that the displacement, I call it as displacement, is small. So
Yes.
we just write down kind of solution. So that this should be like adding some in other terms. Since that the s is pretty small, so that this can be just added. So
But
it's-
like, why do we observe the oscillations? Like, does this moment change based on the displacement?
yes, of course.
Okay, why? Like, why does the moment from?
Okay.
Is it the moment of magnetic force?
Yes, of course.
Oh,
There's
okay.
a torque from the magnetic force. And since every change is because that then this is a rod.
Okay.
Okay, and this is a magnet. So if the magnet force attached to the rod in the lower direction, which means that the magnetic rod is actually the center rod.
Okay.
You can see that the magnetic force is right here, right?
So-
this is the magnetic
Okay.
force. And however,
So you assume it's a harmonic oscillation of velocity. Like
No,
when we neglect these terms, this should be like
Yes.
a harmonic oscillation.
yes.
Okay. What about the other assumptions?
Okay.
Like how
So this
you
is
model
the X.
magnetic force, for example, or you model the magnetic force, but you neglected all these terms and just had this. That's the assumption for harmonic oscillation.
that's the assumption for
What
X.
about maybe the coefficients of frictions? What assumptions were made there? Because on slide 10, I believe there were like different coefficients of friction in the x direction and y direction.
No, and actually you said.
Can you show slide 10?
Like that.
Yes. So
This or this.
slide 10. This is slide 10.
Then this is 10.
Okay, so you have like RZ, RY, Y is
So
the
actually the RZ and RY represents the direction of the friction between a rod and a magnet.
Okay, so you believe that the friction should be different in different directions?
Yes, the friction will be different in different direction due to the velocity will be different in different direction.
Is this the friction force or the friction coefficient?
This is the friction force.
Okay, so I agree that the friction force can be different in different directions. However, like in terms of frictional coefficients, they are the same in every direction.
Yes,
Do
of
you
course,
agree?
of course.
Okay, so how was this friction force calculated?
How was the friction force calculated? So
Did
first,
you measure the friction
yes,
coefficient?
of
that
course
was-
we measure the friction force. So
How was the measurement done?
the friction is about 0.38.
And how did you measure it?
How did I measure it? I didn't show it in my, but actually, I just, this is my rod and this is my magnet. I will attach the force meters.
Okay, okay, I agree. I think this is a valid meaning of measurement of the coefficients of friction. So thank you, we cleared that up. Actually, the coefficients of friction are the same everywhere, but the friction changes due to the gradient of force, correct?
The friction change due to the direction of velocities.
Due to the direction of velocities?
Yes, the friction direction will be changed due to there's the
Does the friction depend on velocity?
Yeah, the friction direction depends on the velocity.
Does kinetic friction depend on velocity?
Yes, of course, the friction direction is a response to the velocity curve. It refers to the velocity's direction.
Okay, so just like because the velocity direction changes, the assumptions use dipole approximation,
What do you mean?
like dipole approximation.
Magnetic dipole?
Yes.
Yes, I'm just using this dipole exception.
Okay, I think that's valid. Now, like, when we explained the assumptions of the theory, let's move on to the slide number 30,
30.
where you have the lines.
Yes.
So you have this equation, and you are saying that these lines are from this equation, correct?
Yes, it should be.
Okay, so
No,
based
no,
on
I-
this, you
I-
have no constant term here.
Sorry, I just misunderstood. Actually, I just put this linear slope here, and I just fix it, and I was using this slope to compare with my view.
Oh, okay, so these lines are just fixed,
Yeah, this,
and you compare to just the
Yes,
slope
I compare
that
the
should
slope.
be equal to this.
yes, yes.
Okay, but still, why doesn't it pass through zero? Because like I would expect that with zero angular velocity, there would be zero climbing rate.
Yeah, this should be.
So why isn't it so? Like we can see that clearly these lines would not pass through zero.
I think that more than that, there might be a minimum angular velocity boundary condition, but however, my motor can reach this is the minimum angular velocity I can reach.
Okay.
So I cannot observe the.
Okay, but I still think that there is some issue with these fits because, well, you should have at least like fitted line that does not have the constant term. You should have just fitted like
Yeah, I agree that I
function
think the constant
constant
for
time x, so that would be better and actually maybe would have more value to the experiment and would be more correct because I don't feel like also fitting it with a constant term.
Okay, I agree that is constant.
Okay, thank you. Let's move on to some other measurements on like graphs 30, 23, 24, or 25.
This between these three.
Okay, 25 maybe. Yes, so why don't we have the predictions here as we have like this
Okay,
relationship?
since this is okay, like since we consider that the fast region is region here, so it actually creates this phenomenon. And actually, this equation, this phenomenon is the self-consistent equation. You cannot actually solve it. We need to use the normal.
Couldn't you just solve for some time average rate of climbing or so, and from that obtain the prediction?
Yeah, that assumption we use just reject the like this phenomenon.
Okay.
We cannot actually use something we have to.
So you did not like account for slip state phenomenon in this equation?
Like, this phenomenon actually consider this entity, but for the actual traffic rates.
Okay, so this is just the term for slip state.
Yeah, that is the main.
Okay, so I think like based on your theory, it should be also calculated and predicted, even though like if there is no analytical solution for this, you should have just calculated it numerically or so, and also like compared the velocity of climbing of depending on some other relevant parameters such as number of magnets are, because I think that's the target.
Zero method will not mainly affect the velocity.
Yes, but like for many of the relevant parameters, other than the rotation velocity, you do not have the comparison, so I think that should have been done. Also, was in the theoretical model something fitted, or did you like just measure everything?
I measure everything.
Also, like the magnetic moment.
If I measure magnetic moment, I can show you.
Okay, sure.
Like here, we just, this is my measure, this is my force sensors, and so I
Okay.
just, my.
Okay, I think like this is a valid measurement of
Yeah.
magnetic moment. I agree. It's nice that you actually do not have any fitting parameters, measured everything, but I would really like to see the comparison of the theory to the experiment on some other relevant parameters than the angular
So I think
velocity.
like all the parameters, you can classify that.
Okay, what about some error analysis? Like how did you account for errors of your measurements? Did you just repeat them multiple times and calculate the standard
Yes,
deviation?
of course, I repeat them 3 times for one experiment, and also you can see this.
Okay,
So we can
I think
do
that is
the
also
error.
valid. And maybe also for the phase diagram, could we also somehow obtain a prediction for that?
For
Or
prediction of
Yes.
this trace diagram.
yes.
No, actually the other here is actually related to like
Okay.
quite hard to study it because that it is related to stage region and which means that the matter of tilt, and I think that is quite hard for me to this kind of tilt.
Okay, thank you.
Sir, time is up.
Thank you. So, for the discussion summary, we first clarified some assumptions of the theory, how the magnetic force was modeled, what is like the origin of the oscillations of the velocity. Then we discussed about friction force, because firstly we thought that the friction coefficients actually changed in different directions, but it was cleared up that just the friction force is being changed based on the direction of the velocity, and it is like not dependent on velocity. It is constant, but like the components change based on the direction of velocity. Also, then we discussed the prediction. Found out that the slopes were, in our opinion, fitted incorrectly and should have been fitted without the constant term. That's why it didn't pass to 0. And also, we would like to see comparison of theory and experiments for other relevant parameters that is stated in the problem statement. And then at the end, we talked about the error analysis.
Let's go to review. Thank you so much for your report and your solution. First of all, for the reporter, did you account for spinning of spinner at the end of the lattice?
What do you mean?
You have the fidget at the end. Did you account the velocity of the spinning mat?
Yes,
spinner?
yeah, of course.
Okay, and position. Did you mention the inertial effect?
Yes, like the moment of inertia of the rod might change like based on the thing that is attached to the end. And the moment of inertia of the rod is present in the theory,
Okay,
so
thank
it
you
should
so
be
much.
accounted for.
Next question. How would you define the rate of climbing?
Since that the gravity, since that the one virtual displacement to the right.
Do we see the displacement resolution of the rotating code, or is it the displacement of the
We just measure by you can see there actually the thing the velocity here. It was response to
how did you measure the
the
velocity?
Huh?
Is it the velocity per resolution of the rotating code?
I need a translation velocity.
Okay, thank you. Can you please define the S oscillations as well as the oscillations in the Y
So we need an
axis?
oscillation.
The S oscillations, yes.
Because there has a precision force and so making a balance of tilt and the tilt too much, you are pressing that there is another magnetic force while you.
Okay, do you think it's a relevant observation?
I mean that is related to your sensitive phenomenon. So it is actually a motion. One of the motion.
According, do you think it's a relevant observation?
I mean, yes,
Planet.
like it can be approximated like this. And I don't necessarily think it explains the slipstick phenomenon where the rod should stop completely, but I believe we do observe some
Okay,
oscillation
thank
of velocity.
For the reporter, can you please tell me that why would you use the fidget spinner? Why is it appropriate for this experiment?
Alright, this one.
Yes, this
So
spinner.
I was used to measure the angular velocity.
Have you weighted the spinner itself
Yes,
without the
I
lattice?
consider that inertia of the.
Doesn't it shift the point of gravity?
No, I just did it because it is actually the back of the sentence actually just right on the center of the man.
So the weight is no significant.
Yeah, that is the
Okay, so the gravity changes. The point of gravity changes.
Yeah, that's what we observe. We consider that as well.
Okay, do you believe that the force that is the most significant is the gravitational force?
No, I don't think so. I think the most important force is the friction between a magnet and a rod.
So the most significant force in our stop is the friction.
Yes, the most.
Okay, thank you so much. in that one today I will review the problem number 4, planning magnets. I think we're all familiar with the problem statement. Okay. Thank you so much for your presentations. I really liked it. The review of the report. The strength we would like to highlight is actually easy to see the rotation of magnets because of the spinner fidget used. But we think it's not as decent to use because it might change the point of gravity and therefore it might affect the planning phase significantly. We've seen the six-slip phenomenon explanation, and we think the explanation was pretty decent. You've spent the amount of time on it. Then mass and equations. We think all equations were decent. Unstable conditions explained clearly. We've seen all the control variables as well. The areas of improvements, the inertial factor of spinner may add up on the total velocity, the net velocity of the magnet, and the friction of the magnet clamp. It wasn't really varied, so we think it's not enough parameters used, not enough parameters investigated. About the opposition, we really like that you spotted the linear graphs because we want to ask the same question. The stated the unclear determined connections to theory and the areas of improvements will say that assumptions were explained clearly by the reporter and science and discussing. Then you didn't really mention this fidget spinner. I mean, you mentioned it, but you didn't really fully discuss it, and we think it would be the interesting point to discuss. The discussion analysis. Would the magnet accelerate? The opinion of the opponent was that the magnet is supposed to accelerate, and the opinion of the reporter was the magnet should not accelerate. We agree with opponents. The acceleration should present as the velocity is varying. We've seen it on the graphs. Then the slide 30, we didn't really observe any limitations. The opponents suggested that we should do some limitations, and the opinion of the reporter, we actually discussed it, and we agree with both sides. Then about the friction direction changes due to direction of velocity, the reporter suggested not all the relevant parameters, and the opponent suggested some of them, which we agree. We would add some more parameters, such as the different obstacles used and different magnetic roads, etc. And we don't really agree with the coefficient of friction being same for all the
Here for in Mark. First of all, the key mechanism of trend method should be the uneven lower force and the friction causing a magnet output. And also, we discuss about unstable triangle due to there's only a common point of it. And also, we use all three directions of motion. We discuss all the directions of motion. And for the number of parameters, we can see that the number of magnets corresponds to the stability diagram, and also the angular velocities and rod and diameters corresponds to the connecting line velocities between the rod and the magnet. And for the distance between the rod, it's actually causing that there's a larger x direction oscillating force, which is caused by the friction. This is pretty important. And for the second part, actually, we quantify that we discuss the slope with mass and the theory, and also though the opposite ratio there should be like we can just use the number solution to solve it, but actually this self-considered inclusion requires a more unknown initial conditions and parameters. It is not as simple as opposed to made it down. That's why you need to see that this is not a symmetry condition, so actually you need to know like the magnetic belt or something. And in all our presentation here, I have no fitting parameter that I have fixed value in case experimental. It's because there's still a lot of like unknown initial conditions and parameters. And for reviewers, you mentioned that the spinner will affect the whole system, but however, first of all, the spinner is actually symmetry, so it won't affect a lot of the integer. And also, the spinner only weighs about 1 gram, so it won't affect compared to the total magnet, it's about like 80 grams or something. And also, you said that we don't think that the magnet will oscillate, but actually, I do think that the magnet will oscillate. I also consider my theory, and I also plot oscillating block for the simple component group. So I think that you do not quite understand for discussion and dedication. That's all my concluding remark. Thank you.
And maybe to the report, how many degrees of freedom do you have in original? How many degrees of freedom do you have in the system in original?
For magnet and 3.
Okay.
The reporter, did you train to speak so fast to read the report?
Oh, I'm sorry that this, but
Did you train? Did you?
yes, I this a little bit too what to say, so I a little bit made my speech a little bit quicker.
Yeah, can you bring up slide 30?
Yeah.
Yeah, I mean, you've got several lines on there. Can you just tell me?
So from the like this like straight line, actually the small number of magnets and the green line actually the large number of magnets. You can see that this actually makes the density of normal force, and the one axis makes this whole magnet. So you can see that if I increase the number of magnets, if I actually can see that the normal force become distributed unequally. So it is actually a normal force distribution.
Okay.
Can you explain me your phase diagram?
Basically,
Yes.
yeah. So
This, what does it explain? I don't understand.
okay, so there's two small number of magnets. We're noticing that there's not enough Raffle force. So we're noticing that the normal force distribute equally. So it can have the rotational velocity. So it won't end up in this region. However, if I increase the number of magnets, it will have. If I notice that the magnets will rotate, so they will turn stable. But if I increase more number of magnets, you are noticing that the Raffle torque will pull the magnet down. So we only have a competing pole in unstable region. In my person, the magnet value descending, and if I just having too much number of magnets, you will notice that the magnet is falling down.
What do you call this a phase? What is the phase diagram?
So here I have the number of magnets and the rod angular velocity. These are the two parameters I control.
And maybe to the point, where does the vector of the angular velocity point generate?
I believe like outwards or like in the plane.
Is it along the axis of the magnet, or is it generally speaking not?
Yes, I believe it should be. As it is constant at the time.
Well, to the opponent, you were talking about measuring the frictional forces, and you drew a diagram with the rod and the magnets. Is that how you would measure the actual frictional force, and which force of friction would that be?
I think it's like the friction between the rod and the magnet, and as you weight it, you can like actually calculate what it
And
shifts.
you would attach the string where you shown it.
Yes, I think it is.
Yes, thank you.
And you should consider like the moments of the torques and this kind of also.
Question to the reviewer. What do you think about the different in the different
I
axes?
think the coefficient of friction will vary during the stick-slip motion because the static friction will dominate when the magnet will build up the energy and then it will slip, and the kinetic friction will dominate. I believe that coefficient of friction will be higher at the static friction.
And for the different direction, y and x direction.
I'm sorry, the S oscillation.
I'll go back one slide to slide 19. Yeah, so you have the equation Vz equals A omega. What exactly was A?
A, yeah, this A.
No, above, this side. Yeah, that equation. But,
Oh, this, yeah, this A. Oh, it's actually to be the amplitude of the phenomenon, because it's that the velocity here is actually oscillating, so this should be an amplitude of it.
so how
So
does-
I don't know this. I can actually solve an
Please answer shortly.
Huh?
Answer shortly.
Or just, we cannot actually.
so it wasn't measured and it wasn't calculated.
Yes, it means you use a numerical calculator to solve the set.
Thank you.
Okay, this one.
4.
Thank you. And the score of the opponent.
So the opponent scores are 7, 6, 9, 8, and 5.
And the scores of the reviewer.
The reviewer scores are 3, 5, 5, 5, and 4.
Thank you. And I have the score sheet, so you can give some comments. For the reporter, we have a high score 26. You want to explain something? For the reporter, yes, you give 6. Okay, thank you. And we have 3, 4 major gathering, please.
I thought you'd done an awful lot of work, but unfortunately, I found your report incredibly hard to understand. You were going at such a pace that more is not more, it's less and less less. The connection as well between the theory that you were proposing and the actual experimental data that you got, I didn't see was there, and the various experimental parameters I didn't think you could measure properly or calculate.
Okay, thank you. For the opponent, Edward,
Yes.
you was 9.
Yeah, basically.
I see.
Yeah. The thing is, I very much agree that the report was really rapid and was very hard to comprehend. And then I noted myself down, like I noted some questions, for example, how did you measure the friction coefficients and which magnetic model did you choose and so on. And then you came up and essentially addressed all these points and I was like, yes, yes, yes. And you could just make tips, adjusting tips, and then essentially the only tips I didn't give you a 10 is that the time management was a little bit off. And yeah, you could have maybe presented a little bit of your more of your own opinion, but I think the choice of topics and discussion points, at least up to my personal opinion, was really great.
Thank you. And Gavin, maybe your part?
I thought your initial questions were fine, but then when we got into the report, your initial discussion was thoughtful, that was good. It picked out that there seemed to be multiple coefficients of friction. I would have been much more interested in the, I didn't pick up on the fidget spinner, why you use that and exactly how it was used. Was it used continually? Then there was a number of magnets, were they attached to the fidget spinner or not? I wasn't clear. Why having more magnets made any difference whatsoever, because you didn't seem to measure that. His diagram for where he was showing the force connection between the magnets that he got, he was obviously lifting the magnets as well, and there was no discussion as to, did he take that into account? I have no idea. So there were just several things I thought, as an opponent, that I think we could have picked out. Unfortunately, yeah.
Thank you, Gavin. And for the reviewer, I think it was 3, because in your presentation, you have the analysis about what the reporter have done and what the opponent have done, do not show much more about your own ability to do the discussion. That's see. And Eric, you do the first.
I give it 5. I must say I was mostly stick to the scoring sheet. I think it was globally between superficial and good. Sometimes with some remark, and you answered correctly to my last what I mean correctly to the last question. I thought it was 5.
Can I comment one thing about the review? I think it would be helpful if you want to full screen.
I put it in my laptop, it was the full
if you see that your reviewer has this problem, you should quickly do something.
It's a group work.